Hi everyone, my name is Lance Bassett. I'm a senior in computer science and I'll be presenting my honors capstone, which is called Infrastructure-Based Detection and Localization of Road Users for Cooperative Autonomous Driving. And so to break that down, that means we are using cameras mounted in the infrastructure, looking down at intersections, to detect vehicles and pedestrians, so where they are in the image in 2D, and also localize them, meaning find out their location in 3D out in the world, not just in the image. And the cooperative portion is that you can have potentially multiple of these sensor boxes and build a whole sort of supervision system is kind of the vision down the line, and have vehicles and infrastructure communicate. So if infrastructure detects dangerous behavior, like somebody's running a red light, it can warn cars, and in that sense they're cooperating and sharing information and computing power. So this project is the actual methods for detection and localization within this larger system. And we do that using two separate but related neural networks, trained separately and run one after the other. Both use this encoder-decoder architecture with a ResNet 18 backbone and have different prediction heads for centers, classification, and corners. That's actually as much detail as I'll go into for the architecture for the sake of time and because people may have various levels of familiarity, but you can feel free to pause it and read for yourself. And instead, I will jump over to this kind of step-by-step pipeline that breaks it down a little bit differently. So like I mentioned, we have two networks. The first one will take in the whole image of the intersection and spit out the object centers and a classification. And then we will generate cropped portions of the image at each of the vehicle centers. And then we send those through our second network, which spits out the corners of the vehicles. And you kind of put these together into the image to get your result. And then there's two things that we do after the prediction. One is the actual localization, which I mentioned before. The model doesn't do that. We use this pre-processed coordinate mapping. So before running anything, we generate a pixel coordinate to 3D coordinate mapping of the scene because we have knowledge of the scene beforehand and it's fixed. And so how we use this is once we have the location of a vehicle in the image, like at a pixel location, we can look at the coordinate map at the same spot, and that will give us the world coordinates of the vehicle in 3D. The other thing we do is corner completion. So the second model will sometimes miss one vehicle corner but get the other three. And so in cases like that, we can use the opposite corner and the center to finish the bounding box and kind of salvage that detection. And so when you put all this together, it works pretty well, we found. So you can see some sample results there. Sorry, they're a little bit small. But here is a table down in the middle there. There's a table that shows how many pixels off our centers are from the ground truth centers, and the same thing for the corners, and also how far off in meters our localization is from the ground truth. And so in our best model, our centers are off by about 3 pixels, our corners are off by about 2 pixels, and our 3D localization error is just over 0.2 meters. And so the method we're comparing here, when I say single stage, is an alternative method that I couldn't fit on this poster, where we have just one network that predicts centers and corners and classifies, given the whole image, which is different than our kind of two network back-to-back approach that we have now. And here on the bottom we have the detection rate, which is about 0.987, and the number missed as well as the number fixed by corner completion out of 1900 in our validation set. And so we can see with 72 fixed, the corner completion does come up a decent amount, so it is helpful. Another thing I will mention is this center jitter augmentation. It's something we do to help our results as a training augmentation for our cropped model. And we call it jitter. So this is where we shift the center and making the resulting crop off-center, like you see in the top left there. The center remains in the center, but the car has been shifted down in the crop. And we add these center crops to our data set to make the model robust to noisy centers, with basically the goal of making it so that bad center predictions from the first stage don't ruin results of the second stage. And we can see that the model trained with jitter from these graphs is much more robust to poor centers. So as we move right on the graph, the models are tested with centers that have been shifted more and more and are noisier and noisier. And without jitter, the pixel location of corners, the localization error, and especially the number completed, as well as the detection rate, they all get worse as you add more noise. But for the model trained with jitter, you can see that results are relatively constant, even with the maximum amount of noise, which is a significant amount. So that's a very important augmentation to make the model more robust. And so that's most of our methods and results, and I'll kind of summarize now the good things, the advantages about our model and our methods. So the way we do it is we have these two separate stages, and one of them is trained on crops of the image. And that's helpful because this model is much more universally deployable. So meaning you could train it on one or a few scenes and then deploy it to another with a decent amount of confidence. Because as you can see between these images, there might be a high variability between intersections. So when you look at the whole thing, it looks very different. But when you zoom in on an individual vehicle and you take kind of the background out of play, there's very little variability. So these could, the second stage could theoretically be trained and deployed in different places much easier. Additionally, having these two separate stages can allow the second stage to refine the first. So if we classify objects in both stages and the first stage thinks a fire hydrant is a car, we'll crop that fire hydrant and we get a chance to correct that in the second stage, which will see that crop and then be able to say, no, this is not actually a vehicle, and then we can throw that detection away. And these, I will mention these first two things are advantages. In theory, we have to test the deployment across multiple scenes and the refining. So that's part of our next steps. Also, I will say that this approach takes advantage of the fact that we have a fixed scene from up in the intersection, as opposed to being from the point of view of a moving vehicle. And so we take advantage of this with the pre-processed coordinate map for localization. So we've tried to have the model itself predict the XYZ coordinates of the vehicles, but that's a pretty difficult task for a network. So the coordinate map lets us use the unique fact that our cameras are fixed. And then because it's pre-processed, it's not a problem to sacrifice time for accuracy. So if we want to use a very, very complex method to map out the surface of the road within reason, that's really okay, because all we have to do at runtime is read from that already generated map. And I'll also say that when you compare this to the single stage approach that I mentioned in those tables, it's much, much simpler. Before, with the single stage, we had to do a bunch of comparing and matching of corners, because when you look at the whole image and you have a bunch of corners, none of them really are inherently belonging to any of the vehicles in the image. So you have to go through and find the best matches. Here, you already know you're cropping it for a single vehicle. And then when the second model predicts the corners for that, you know those corners belong to that vehicle. And that's most of the work, but what we're looking to do in the future, you might have noticed that our data was simulated. So the next big step is translating this to real data and making sure the performance is comparable. Real data is just messier and noisier, so we probably expect some sort of performance hit, but results are very, very good right now. So even with a performance hit, we would expect to be within our goals. And also because we're looking to publish this, we may want to look at what results other people have gotten for 3D localization in scenarios like this and see how our results compare. And like I said, those two things I mentioned before, the universally deployable cropped model and the second stage to correct the first, is something that we still have to implement. But in theory should work, so that's also part of our next steps. And we've also thought about different methods of calculating the crop size for the second stage. So that's something we do. And it's important that crops contain the car completely, but also don't contain too much of the background or other cars, because that's confusing to the model. So that's where we're going. But overall, this project has been very fun, and I've been very happy with all the opportunities I've gotten to learn and to try new things. And I'm looking forward to continuing this project in the summer. Thank you.